بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. So today we're going to start chapter number 5 about linear regression. And in the previous lectures, we have completed several important topics about data science. We have introduced the concept of loss function, about the risk minimization. We've made several examples. We talked a lot about linear regression, but from the perspective of how to create and understand the loss function and how to optimize a particular linear regression problem. We did also for several other types of predictive model like logistic regressions. So today we're going to talk again about linear regression from a different perspective. And it's from more application perspective on how we can use it to solve some kind of real world problems and how we can understand the performance. So imagine now you have built a good linear regression model. You have calculated the coefficients, and now you would like to know whether your model is actually good. Can we interpret the results? How can we interpret the results and the performance of that linear regression model? And in this first lecture, we will just introduce the very simple linear regression model, which has only two parameters, beta 0 and beta 1. So just simple line for only one feature. So this lecture is based on the following textbook, An Introduction to Statistical Learning with Application in R, and more specifically, it's chapter number 3. And this is a very nice introduction to the concept of linear regression. So we're going to start from a practical example, which is about an advertising sales versus the sales data set. So you already know that people, when they want to increase their sales, they're going to refer to advertising, and they can advertise through different channels, like, for example, through social media or using the radio or television or newspapers, and every type of media would have a cost. And the question here is whether this advertisement or advertising campaigns will help to generate more sales and more revenues. So this is basically a problem. And it turns out that linear regression can be used for these type of examples, just for example, to predict the sales based on the expenditure on advertising and also the impact of different type of advertising categories on the sales and on the revenues. So we're going to consider a very popular data set that you can find on Kaggle, and it's called Advertising Budget and Sales. And it has different, so 3 features, which is the budget spent on television or advertising, and the budget spent on radio, and the budget spent on newspaper. And here we have the outcome, which is the the sales, and they are expressed in $1 million. So here they are expressed in $1,000. And we have the sales expressed in $1 million. And the objective now is how we can derive a linear regression model based on the advertising data to predict the revenues and the sales. Is that clear? And the data set contains 200 data samples and 3 features and 1 target variable. So this is just a sample of this data set. And here I have plotted 3 different plots that shows the television advertising versus the sales. And here we have the newspaper advertising versus the sales, and we have the radio advertising versus the sales. So what do you observe here? Is there any correlation between the advertising and the sales?
Yes, you can see correlation, a positive correlation.
Okay, so we can see a positive correlation. And here, okay, just to make things simple, maybe we are able to assume that is there any relationship that seems to be a little bit linear? Which one seems to be like a clear correlation here that is positive?
Radio and sales.
Radio and sales, but TV looks even...
Sales and TV.
Yeah,
But
sales and TV. Yeah, so we can see like stronger correlation between TV and sales, a little bit less for radio. And the newspaper, you know, it's a little bit more scattered, but we can see that there is an increase overall. Okay, so now in these type of situations, we would like to assess the impact of advertising on sales. And there are multiple questions that we can ask at this stage. For example, is there any relationship between the advertising expenditure and the sales revenues? Another question would be, for example, how robust will be this correlation? Now, if we see here, we have 3 correlations. They are not with the same robustness. We can clearly observe that, for example, TV correlation is more robust than, for example, newspaper and sales, or a little bit more for radio and sales. Okay, which advertising media significantly impact the sales? So these are questions that we can solve using, for example, these scatter plots, or also by making predictive models. So these scatter plots give us an initial idea, but now my objective is to make a predictive model that, given a certain expenditure on a particular advertising media, I can estimate what will be the sales increase or the revenue increase. Okay, so other questions like, what is the sales impact for each advertising dollar per medium, or how accurately can we forecast the sales based on the current advertising level? So this basically, the accuracy of the forecast is based on the accuracy of the prediction model that we will derive. Of course, in this lecture, we are going to start from a very simple model, which is simple linear regression. And there will be some tools that we are going to introduce today that will tell us how accurate this predictive model is. And assessing also the true linearity of relationship. Is the model really linear or probably not really linear? Okay, is there any particular theoretical model that actually maps the relationship between the input and the output, and also the interaction effect among the different advertising media that enhances the sale? Okay, so let's start by the problem formulation. Now, in this particular case, now, for example, between the TV and the sales, we can observe that there is kind of a clear positive relationship that could probably reasonably be estimated to a linear regression. So we're going to start from that assumption. We're going to assume, for this particular case, that we have a linear regression between TV and sales. And now our objective is to find what is the line, okay, coefficients, the coefficients of the line. And usually the coefficient of the line will be expressed as beta 0 and beta 1. So beta 1 will be like the slope, and beta 0 will be like the bias or the constant. And here we have a response Y, which is our sales, and a single predictor X, which is our TV advertising budget. And the symbol here, it means that we have an approximate relationship. I mean, whatever line I will find, it will not be a perfect fit. There is kind of a noise that will be around the line, but I want to find the best fit possible for this particular situation. And in marketing analytics, such as predicting the sales, okay, it's one of the practical applications. Like we have in our case, the correlation between the T advertising budget, which is our X, and the predicted sales, which will be our sales here, our Y, target output. So the parameter beta 0, it's called the intercept. And you will find this in any linear regression example. Even now, when we work in Python and you see the result of the optimization, you will find intercept and slope. So slope, of course, is the slope of the line. And the intercept is the intersection with X equal to 0, or Y. X and Y equal to 0, yes, here. So for X equal to 0, I will have a particular Y. And now I can interpret that if I don't spend any budget on television, okay, the sales will be around 7.03 increase. Okay, the increase will be around $7.03 million, or the unit of the sales. So, and the estimation here, we want to derive what is beta 0, the best fit for beta 0 and beta 1 estimated using the training data. So here we have 200 samples. And based on the 200 sample, I want to estimate beta 0 and beta 1. And the prediction formula will be Y hat equal to beta 0 hat, which will be empirically derived, and also beta 1 hat, which will be empirically derived. and you want to predict the future sales based on the specified TV advertising budget. Now, just a practical tip here, when we want to estimate the coefficient using Python, and in particular the NumPy array library, there is a nice function that is called np.polyfit. It takes x as the input or the features, y as the output, and 1, which is the order or the degree of the polynomial. So if the degree is equal to 1, it means I have a simple linear regression, just a line. If it is 2, it means I have a quadratic regression. If it is 3, so it will become cubic, and so on. Okay, so you can use this function in order to find the estimated value of the slope, which is denoted as m, and b, which is the intercept. Okay, and basically it will apply the optimization that you have introduced in the previous lectures. So here I want you to always recognize the slope and the intercept as two keywords related to linear regression. So how to estimate the coefficient in linear regression? As we already introduced, our objective is to estimate beta 0 and beta 1, okay, that best fit the data that we have, the sample data that we have. In our case, we have 200 sample data from the features, which is the advertising, and the target output, which are the sales. And here we introduce the concept of the residuals, or what we call the residual sum of squares. And this is basically a very similar function to the MSE, the mean square error. The only difference is that this is a sum of errors, and the mean square error is just the average. So if I go to this slide, when we talk about convex optimization, and in the beginning we talked about the mean square error, which is equal to MSE 1 divided by n, and the sum of errors. So the RSS, which is the residual sum of square, is just this term, only this term. And basically optimizing the RSS is the same thing as optimizing the MSE, because the derivative will be equal to 0, and this is just a constant, which is independent from the weights, okay, from beta 0 and beta 1, so it will be eliminated. So saying that but in the language of linear regression, usually when we talk about optimization, we usually use the residual sum of squares, but basically it's the same as the mean square error, because the only difference is that you need to define by a constant, which is the sample size. And it's primarily used to calculate other metrics for fitting the model during the training phase. And this one is used for a loss function for regression model to evaluate the model performance. Okay, so look at here, of course. Now, when you see this curve, you understand that we are going to use a gradient descent. So in the beginning, I'm going to start by a random value of beta 0 and beta 1. These are our weights, beta 0 and beta 1, the intercept and the slope. We're going, for example, to start at this location or this location. Then using gradient descent is going to converge to a point with the minimum loss value. So this is the same thing in the right side, in the left side, but it's presented in 2-dimensional, and the third dimension is presented as a gradient of colors. So when the color is, for example, when the color is yellow, it means I have a high error. And when the color is dark, so I have 0 error. So here, it's basically I have 0 error, which is around 7 and 0.005. And we will find that these are actually the optimal values when we're going to apply it on the data set of the advertising versus the sale. So using the data set that we have for this very simple example, because we have like simple linear regression with only 2 parameters, beta 0 and beta 1, we can calculate beta 1 as using some mathematical computation. We can prove that beta 1 is equal to the sum of all xi minus the sample mean multiplied by yi minus the target mean value, and divided by the sum of xi minus the sample mean square. So mathematically, this can be proven. Okay, I can make this sum to find beta 1 and also beta 0. So here, this optimization is done not through learning, but through a numerical optimization approach. So here we didn't use a learning approach using gradient descent and training loop using learning rates and so on. We can do that. So to minimize the MSE. But this is because this problem is very simple, so we can solve it numerically and mathematically can be proven. And the same thing for the intercept. Once I find the estimated value of beta 1, I can calculate the estimated value of beta 0, which is the intercept, which is equal to the sample mean of the target output value, okay, which is the average of all y's, minus beta 1, and this one is the average of the sample features. And using our advertising data set, applying these formulas, we can find that beta 0 is equal to 7.03, and beta 1 corresponds to 0.0475. And how can we interpret this result right now? It means for each increase of $1,000 in the TV, this will be associated to an increase of 47.5 units in sales, because this is the slope. This indicates how strong the sales will increase when we increase a unit of the budget. So the unit of the budget here is $1,000. Okay, so the greater this number, the more correlation and the higher impact of the TV advertising will be on the sales. Is that clear?
Yes, doctor.
Okay.
Doctor, can we say that beta 0 is the number of sales without any advertisement?
Yes, and this is what we have introduced in the beginning, because when the advertising is 0, the value will be the intercept. So we will have here 7 unit in sales increase. That's correct. And this is basically the same point that we will find here. So this point corresponds to 0.0475, and in the y-axis, it corresponds to 7.03. This is just a visualization, and the same thing is here, okay? It corresponds to beta 1, okay? It's dark over dark, so it's not really clear, but it's basically the same values. So now, once we have built a model, now we have determined the coefficients, beta 1 and beta 0, and we want to assess whether our model is accurate or not accurate. Okay, so in order to assess the accuracy of a model, we need to assume that we have already a theoretical model that mapped the features to the target output. Okay, so let's assume that we have a model. We start from a model that is beta 0 and beta 1, and beta 0 and beta 1 are the correct coefficients of that model. But you know, any model in reality will not be a perfect line. There is always a noise around a linear predictor, a linear regression predictor. So this noise usually is modeled as an epsilon term. It represents the deviation of the actual points, the deviation of the blue points from the prediction line. Okay, and of course this one, it has an average of 0, and it has a variance that is greater than 0. And this is why we have here, this point will be scattered around the line, because we will have a variance that is non-zero. But the average will be 0. If we average all these points, we have some points on the top, there are some points here below the slope, but averaging them, we will have a mean that is close to 0. And usually we assume that this error, or this epsilon, will be a Gaussian distribution, a normal distribution with 0 mean and a certain variance that is non-zero. And the objective is actually to estimate the function fx, okay, that will be the best fit to the real coefficient beta 0 and beta 1. And look now, this plot, which is here below, this shows the residuals, or the errors around. So the average line is the average of the residuals, which is equal to 0, and we can observe that these residuals will have a variance that is greater than 0, will be scattered around the average 0 line here. So a mean 0 random error term, it captures what the linear model cannot explain, okay, because this line, okay, it's a good predictor, but it cannot explain this randomness, the noise that cannot be captured by the regression line. And of course, when the variance is high, So the noise will be much higher, and the error, which is the deviation from the regression line, will naturally be also higher. And the objective here is to try to find an approximation of a linear regression model that will approximate the true relationship. So the true relationship is the beta 0 plus beta 1. Okay, and we want to find the true relationship when f is linear. And this assumes that x, the term epsilon, which is the error, is assumed to be independent of the predictor. Okay, they are theoretically independent. So in order to make an estimation of beta 0 and beta 1, okay, let's remind the population mean and the sample mean. Because, you know, if we assume, for example, that we have a true relation, for example, 2x plus 1, let's assume that this red line is the true relation that represents 2x plus 1. But we want to estimate this true relation based on our data. So if I take a sample of 100 value, and then I will make a regression line that perfect fits these 100 values, I will find an estimation of beta 0 and beta 1. So if I take randomly other random values, I will fit another approximations. So you can observe these dashed blue lines. They represent an approximation of the true relationship based on the data that it was trained on. Because the coefficients here that you will obtain will be based on the sample data. So if you take different samples, you will find close estimation, but they are not the same. Okay, but using the theorem of central limit theorem, okay, in this case, we can, in principle, this means will converge to the population mean. Okay, and here the same thing, we will have a population and sample regression lines. So the population regression line is the theoretical one, is the perfect model, is the true relationship. This is the population regression line. And all other dashed lines that are in blue, they represent the sample regression line. Okay, so I think you understand this. It just because we're going to make an estimation of the population regression line, and it serves as a practical tool to approximate the population line, aiming to minimize the sum of the squared differences or sum of the squared errors between the observed values and the lines. So the objective of the estimation is to minimize the residual scale errors. And finally, we will find these derivations as we already introduced in the previous slide. Is there any question?
No, sir, no question.
Okay. So since we are going to make an estimation of beta 0 and beta 1, these estimators must be unbiased. So what is an unbiased estimator? An estimator is unbiased if the expected value equal to the true value of the parameter. Okay, and what is the expected value? It means if I find beta 1 from one sample, okay, another beta 1 from another sample, another beta 1 from another sample, if I make their average, when I have so many average values collected, so it will converge to the true population mean. And this is basically, we apply the central limit theorem, okay, which says that the averages from different samples, it converge to a normal distribution. Okay, and the average of the average will be the population average. I hope that you remember this theorem. Okay, so this will actually, yes.
Why do we regress on the samples instead of just regressing on the population, entire population?
No, you know, population, it means you have an infinite number of data. Whatever sample, if you have million size data set, it doesn't represent the population, it's just a sample. But usually, okay, when you train, you don't train on the whole data set. You are going to train just on a sample because you will put another sample for testing.
Right.
You remember the cross-validation.
Yes.
Okay, so even if you assume that you have a population, you're not going to use it completely. And we don't usually have a population because we need to have, like, let's say, whatever data you have, you might bring another data. Only if your data is just static, it cannot be different from what you have. But in reality, usually any data that we have is just a sample of the real world.
So we can't call the data set the population because it's not
We
the
cannot.
population.
It just,
It's
if
just
you
the
have,
sample.
if you have a data set of images for faces and it has
Yes.
7 million pictures, is this a population mean? It has many other pictures of people that is not in the data set.
Yes.
So whatever data set is, usually it's a sample. It's a sample by itself. And the theoretical value, the theoretical average is unobservable. It's theoretical, okay? And this is why we need to make an empirical estimation of this theoretical average. Okay, so to understand this, we need to calculate the standard error in the regression analysis. Okay, so what is the standard error? When you calculate beta 0 and beta 1, of course, these estimators are random variables. And we will assume that if we have an unbiased estimator, their average is going to converge to the population average, but they will have a variance which is calculated as follows. So the standard error of beta 0 will be the square root of sigma square divided by the sample size plus sigma square and the sample mean square divided by the sum of xi minus the sample mean square. So this represents the standard error in the intercept beta 0. And the same thing, we can calculate the standard error of the slope beta 1, which is equal to the square root of sigma square divided by the sum of xi minus the sample mean square. And what does it represent sigma square? It represents the variance of the error. And the bigger the variance, the bigger the standard error of the intercept and the standard error of the slope. So when you have points, like for example, if I go back to the data set here, which one has the highest noise?
The newspaper.
And which one has the lowest noise?
TV. TV
TV,
shifts.
yeah. So you understand things. Now, if I assume that I have a linear regression here, the plus epsilon, which represents the error, it has the highest variance, the highest sigma square. And this one, it has the lowest sigma square. What does it mean? If I provide the regression model here, the quality of the line, okay, or the performance of the line will match better the prediction between the TV and the sales more than what we will have it between the newspaper and the sales. Does this make sense? And of course, you know, when we have the variance of the standard error, we can calculate the confidence interval, okay, at 95%. So here, what you see in the gray line, this represents the confidence interval of the regression line. So at 95%, all our regression line that we will estimate, they will be between the upper line in gray color and the bottom line in gray color. So we will have multiple, maybe an infinity of possible regression lines. And they will all fall with 95% of confidence between these two borders.
So here the confidence means that 90% of the 95% of the lines are going to fall between this interval.
Exactly, yes. Yes.
Okay.
Okay, so in regression analysis, we use the concept of hypothesis testing. So hypothesis testing is one of the theories that is in place to verify whether a particular assumption is correct or not. So the objective is to evaluate if the observed relationship in the data reflects true relationship or it is just due by chance. Okay, it's not because there is a true relationship. And there are some tools that help actually to validate this hypothesis testing. And this is crucial for validating the influence of the predictor in a regression model. So to formulate the hypothesis, usually we formulate what we call the null hypothesis, which we denote as H0. And here, null hypothesis, it assumes that there is no relation or there is no effect between the predictor and the response. There is no relation between X and Y. In our case, it assumes that there is no relation between TV and sales. And this means mathematically that beta 1 is equal to 0. The alternative hypothesis, which we usually denote as HA, it assumes that there is an effect and that beta is different from 0. So how can we validate that the null hypothesis is true or the alternative hypothesis is true? So let's apply this on the TV advertising data. So now, using a Python code we can actually derive a model and we can obtain the following summary. So this summary that you will find here, it provides you several information about the performance of the regression model with respect to the data that was used to build that model. And so in our case, the purpose is to determine if the TV advertising has a measurable effect on the sales or not. So formulating the null hypothesis, H0 here will mention that the TV ads have no effect on the sales, assuming that beta 1 is equal to 0. And the alternative hypothesis, TV ads are positively affects the sales and beta 1 is different from 0. So when we look at beta 0 and beta 1, okay, so we will find that the slope basically here, of course, it's different from 0. It's between 42 units and 53 units. But still, these values, the 0.0475 is a small value. So we need a kind of threshold to determine whether this value would be considered as 0 or will not be considered as 0. So whether the null hypothesis is correct or the alternative hypothesis is correct. So how can we understand this? Usually we have a particular parameter that we call T statistics, and I will introduce this in the next slide. It has a value of 17.67. And usually if this value of the T statistics is high, is significantly different from 0, this means that there is a relationship between the predictor and the target value. So this means here that it's highly unlikely that beta 1 would be different or would be equal to 0. And we reject the hypothesis H0 and we accept the hypothesis HA. So what is T statistics? We call it test statistics, or sometimes it's T statistics. It is used in linear regression to determine the credibility of the null hypothesis. It means the credibility whether there is no effect between the predictor and the output, or in our case, between the TV and the sales. So it is calculated as the estimated value of beta 1. And if you remember, the estimated value of beta 1 was 0.0475 minus 0, and we divide by the standard error of beta 1. And this measures how many standard deviation beta 1 is away from the hypothesis value under H0. So the critical value now derived from the T distribution, it depends on the significance level. And usually if the value of T is very high, like in our case, we are going to reject the null hypothesis and accept the alternative hypothesis. Another also metric that is used in regression analysis is called the p-value. And the p-value is also evaluated into the output of the linear regression model performance. And in our case, look, it's very, very small. It's 1.40 E minus 35, and here it's for the slope, it's 1.46 E minus 42. So how can we use the p-value to determine whether there is a relation between the predictor and the output? So if the reported p-value is less than 0.001 for the coefficient of deviance spanning, this means we have an extremely low probability that the strong relationship is due to randomness. So saying it differently, it means that we have a strong probability that is confirmed between the predictor and the target output. So looking at the value here, we will find these values are very, very small. They are much lower than 0.001, which is the critical threshold. So this confirms, again, the result that you have obtained from the T statistics, and you can confirm that the null hypothesis is rejected, and we accept the HA hypothesis that there is a strong relationship between the TV advertising budget and also between the predicted sales. Okay, so and this summarizes actually the theory between the p-value. P-value is the probability of observing results at least as extreme as those actually observed, assuming that the null hypothesis is true. And we usually have statistical significance. So in this case, sometimes we assume that it's 0.05 or 0. So we have a critical value that will tell us the threshold, whether the null hypothesis will be accepted or rejected. Okay, so we come to the end of the lecture, and to summarize, when we derive a linear regression model, we have different tools on how to assess the relationship, okay, the strength of the relationship between the predictor and the target outputs using the t-statistics or using the p-values. Of course, there are several other metrics as a result of the performance of a linear regression model, and we will discuss these metrics in the next lecture, inshallah. Is there any question?
Yes, you said
Yes.
that the p-value,
Yes.
if the p-value is close to 0, then we accept the H0 hypothesis, correct?
No, if it is if it is smaller, very small value, so we will reject.
Oh, so it's very small, we reject H0.
Yes,
But
like
if
in
it's
our
high,
case.
we accept it.
We accept it. Look, this one is very small. It's really very, very small. It's smaller than this value, or 0.05. Okay, so in
But
this
the
case, we
opposite is
accept the
for
null.
the t-statistic. If the t-statistic is 0, we accept.
So no, same thing for the t-statistics. Yeah, it's the opposite, yes.
Calculate p0, I mean p-values, or just understand how it is used.
Yeah, it's basically it's the opposite for the t-statistics, yes. Okay, so the t-statistics, if it is very high, we reject the null hypothesis. And for the p-value, if it is very low, we reject the null hypothesis.
Okay, thank you.
Okay. Okay, thank you very much. And inshallah, we will have a lecture on Saturday.